Hello and welcome back to Hilbert Spaces, the video series where we talk about topics in functional analysis concerning inner products. And in today's part 4, we will talk about the so-called parallelogram law we have in inner product spaces. But before we start with the details, I first want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please use the link in the description to download additional material like quizzes, PDF versions and books. Okay, so the setup of this video is the same as in the last one, which means we just take an inner product space, so the completeness of a Hilbert space is not needed here. So the essential part is just the inner product, and please don't forget, each inner product always induces a norm. To get this, we just take the inner product and put the same vector twice into it, and then we get the length of x with respect to this inner product. So this is the definition for the induced norm, and to make it clear, I will put the inner product into the index. And please note, we have a square root involved here, which means often in calculations, we will calculate with the norm squared. Indeed, we can immediately do that, and then we get the so-called parallelogram law. For this, we take two vectors x and y, and then we put the addition into the induced norm. And we do the same for the difference of the two vectors, and then we square the norms and add them up. Indeed, this whole thing is not so complicated. We can immediately visualize that in a picture. If we have the vector x and y, then we find the addition vector here. And on the other hand, the difference is found there. And now you see what we did on the left is in this picture just the length of the one vector squared plus the length of the other vector squared as well. In other words, we just want to know what is the sum of the two squares. And this one we can just calculate because we know the norm is just given by an inner product. So we can rewrite the whole thing as that, and this is really helpful because we know the properties of an inner product. Most importantly, we know that we have additivity in both arguments. Hence, for the first term here, we can just pull out the additions and then we get back 4 parts. And obviously we have a similar thing for the second term, just with 2 minus signs. And this one immediately tells us that these parts in the middle here cancel. So the only things that remain are the inner product with x and the inner product with y. And there we already know, these ones we can simply write as the norm squared. And with that we already have our result. The two squares added are given by two other squares added just with a factor 2. And exactly this is what we call the parallelogram law, and it holds for any inner product space, as you can see with this simple calculation. And of course the name comes from the picture above. In any parallelogram, the squares add up like that. If you want to visualize it even more, we take the area here of the big square and add it up with the area of the small square there. And then on the other hand, we can also calculate the areas that are given by the squares from the vectors x and y. And at this point we already know we have to multiply these areas by 2, add them up to get the same result as the left hand side. So you could say this is an equation that talks about all sides in a given parallelogram, but actually it tells us something about the squares of these sides. And moreover, this relation is true no matter which Hilbert space or inner product space we choose here. However, there you should immediately note that in the statement of this parallelogram law, the inner product is not used at all. We just need the norm. And exactly this leads to a natural question: can the parallelogram law also be satisfied in a general normed space? And now it's not hard to see that in a general context we cannot have that, but maybe there are some special norm spaces that satisfy this parallelogram law. However, now it turns out that we already know these special normed spaces. In fact, these are exactly our inner product spaces. So let's formulate that in a precise way which means we take a general normed space X. Hence, this norm symbol here does not have to be induced by an inner product. It just has to satisfy the usual properties of a norm. Moreover, now we also add the assumption that the parallelogram law is satisfied for this norm as well. This means that we have our equality from before for all x and y in our vector space X. Exactly this is what it means that the parallelogram law is satisfied for this normed space. Therefore, you could just say that the abstract geometry this normed space describes still has this nice property with the parallelograms. However, this property is actually already really restrictive for the geometry, because what we get is that in that case the norm is already induced by an inner product. This means we can find an inner product on the vector space X such that this induced norm is already equal to the original norm. So you could say there is simply no choice, such a normed space has to be an inner product space as well. And of course, by the calculation at the start of the video, we also know that we have the converse implication as well. Therefore, the important takeaway from this video is that the parallelogram law is equivalent for a norm being actually an inner product. In addition, you should know that in the last video we have already learned how we can write down this inner product. We know the so-called polarization identity, which tells us that we can write down the definition of the inner product by just using the induced norm. More concretely, for our special norm here, this difference will define the inner product on X. However, please note this only holds for the real case. The complex case is a little bit longer. But it's not really more complicated, it just has two terms more in this sum. So this is all we need. Knowing the norm gives us the inner product with two inputs on X. So this whole thing is quite nice because it reduces an inner product space as a special case of a normed space. And in that sense, a Hilbert space is also just a special case of a Banach space. In short, we can just say a Hilbert space is a Banach space where the parallelogram law holds. In fact, this is such a nice description that one could choose that as the definition of a Hilbert space. But of course then you also have to combine it with the polarization identities here. Okay, so now we've reached the point that we have to talk about the proof of this proposition. And as already mentioned, the one direction of this equivalence we have already shown before. But now the thing is that the other implication is not so easy to show. This means we will need some time for that, and therefore I will put this into the next video. So you already know the program for the next time, and I really hope you come back for that. So thanks for listening, and I wish you a nice day. Bye bye.